In this video, we'll verify that the given differential equation, which is already in differential form, is in fact exact, and then we'll find its solutions. In order to do that, we need to recognize the form that the equation is in. We've got it in differential form. We've got m dx plus n dy, where m is equal to the coefficient of dx, and n is equal to the coefficient of dy. It's exact if there is a potential function, f, a function of two variables, and what it means to be a potential function is its partial derivative with respect to x is giving us this m coefficient, and its partial derivative with respect to y is giving us this dy coefficient, which we are calling n. In order to check if it is in fact exact and there is a potential function, we use the fact that mixed second order partial derivatives should agree. If I was to differentiate m with respect to y, and there really is a potential function, I would be differentiating fx with respect to y, and I'd be looking at a mixed second order partial derivative of this potential function. Because they agree, it should be the same as fyx. But fy is equal to n, so what we should be seeing here is nx. So in order to check, we should compute the partial derivative of m with respect to y and the partial derivative of n with respect to x and see if they agree. Well, let's do it. If you calculate my, looking at the formula we have for m, you get 6x minus 4y. Now take the partial with respect to x of n, and you get the same thing, 6x minus 4y. Those two formulas agree. Therefore, our differential equation must be exact, and therefore there's a potential function f, which we're now going to find. What do we know about f? Well, its partial derivative with respect to x should be m. So we know m. Let's write down what it is and set the partial derivative of x equal to it. We also know its partial derivative with respect to y should be n, and I'm written down the formula we see in our differential equation for n. So we know the derivatives of this function. We should integrate then in order to find the function itself. It doesn't matter which variable you integrate with respect to, but I'm going to choose to start by integrating with respect to x and see if we can recover our function f. So I'm integrating fx, which is m, and I do that term by term here. F is x squared plus 3x squared y. I'm just treating y as a constant in this integration because it's the integral with respect to x. We're talking about partial derivatives here. And I integrate the last term, it'll be minus 2x. Now keep in mind there's a constant term, but in the context of differentiating with respect to x, constant means a function of y. So there can be any expression here that has y in it. I've called it g of y. It could be anything here as long as it only involves y. It is constant in this context. If you differentiate the thing in the box here with respect to x, you'll get what's in the parentheses above, in the integral above. So there's a formula for our potential function, but right now it still has this unknown portion, this g of y. We've used this first equation. We're now going to differentiate our potential function with respect to y and compare because we know what the answer should come out to be. So now let's differentiate our boxed formula with respect to y. When you do that, the x term will be 0, the x squared term will be 0. When I differentiate this term with respect to y, I get 3x squared minus 4xy. And then I've got to differentiate this function of y. That's what I'll just call g prime of y. It's its derivative that's there. We know what this should come out to be. This should come out to be our n expression, our coefficient of dy. So we should set it equal to that and compare. And if you see, we have the same terms, except for this last one is minus 2. Well, that must be our g prime of y. So g prime of y is equal to minus 2. To find g of y, we integrate that with respect to y, because it's a function of y, and g of y then is minus 2y plus any constant. So a particular potential function is obtained by taking our formula above and letting g of y be equal to minus 2 I'll take the constant to be 0 because I only need any particular potential function to generate this differential equation. So here's a potential function that we've just found. The solutions to the differential equation are implicitly given by setting the potential equal to 0. So in this case, I'm going to set x squared plus 3x squared y minus 2xy squared minus 2y, our potential function, equal to a constant. Any function y that satisfies this equation is a solution to the differential equation. Unfortunately, these equations are given implicitly, and that's typically the case for exact differential equations, but I'll show you on the next slide here how you can solve this explicitly for y in this particular example. So let's see if we can find explicit solutions. Here was the implicit solution. Observe that this is in fact quadratic in y. We're trying to find y, and in fact what I see here is I just see y, I see y squared, I see y, and everything else is not involving y. So it's in fact a quadratic equation in y. Let's rearrange it to make that very clear. The coefficient of y squared is minus 2x. The coefficient of y is 3x squared minus 2 times y. And then everything else is constant with respect to y. In other words, there's an x squared term, there is a constant term. If I bring them over together, that represents the constant part of the expression. In other words, the coefficient of 1. And that's equal to 0. And we can now use the quadratic formula to find what y is explicitly. Y is equal to, and I'm writing the quadratic formula out in its familiar form, but here minus b, or b is the coefficient of y, a is the coefficient of y squared, and little c in the quadratic formula is x squared minus c. So you just use the quadratic formula with those expressions, minus b plus or minus b squared minus 4ac, and then I divide by 2 times a, and there is an explicit formula for y. Just cleaning it up a little bit. Not so important, but if you simplify what's under the radical, you get that expression, and there are explicit solutions to the differential equation.